Okay, this next one is another first order reaction. This one is going a little bit backwards. In this case, the first thing that they give us is, well, they tell us that it is first order, and they give us the half-life of the reaction. So it says, what is the rate constant of the reaction? So we know that if it's first order, the half-life is equal to 0.693 divided by K. We're looking for K, so if we rearrange that equation, it's going to be 0.693 divided by my half-life, which is 0.693 divided by 17 minutes. And that's going to give me a rate constant of 0.0408, 1 over minute. That's my rate constant for this reaction. All right, so then if you had a bottle of hydrogen peroxide, how long would it take for 86% to decompose? All right, so in this case, what they're doing is they didn't give us a starting amount, but they tell us that 86% of it is going to decompose. So I'm going to say that the concentration of peroxide initially is equal to 1 gram. If that's true, if that's my initial concentration, 86% is going to decompose. So my concentration of hydrogen peroxide at a later time t, is going to be 0.14 grams. That's 86% of it decomposing. That's how much I would be left with. And I just subtracted 86% of 1 from that. We know that it is a first order, and so we can use the integrated rate law. Went to the wrong slide there. We can use the integrated rate law, and so that's ln of hydrogen peroxide minus, at time t, is ln of minus hydrogen peroxide initial. I don't know what's going on there. Okay. Okay, it obviously does not want me to write up there, so let's not. So ln of H2O2 minus, at time t, ln of H2O2 initially equals negative KT. And we're looking for time in this case. So ln of the concentration at time t is going to be 0.14 grams minus ln of 1 gram for that guy equals negative 0.0408, 1 over minute times t. And then all I have to do is solve for t. I get that it is t equals 48.3, and the units are in minutes, since that's what K was in. All right, then in part C, it says if you started the reaction with 0.1 molar hydrogen peroxide, what would be the hydrogen peroxide concentration after 15 minutes? So again, we're going to use that integrated rate law. And so we're going to be solving for the concentration of hydrogen peroxide at that later time, 15 minutes. So that's equal to negative KT plus the ln of the initial concentration, which in this case, we'll just go ahead and put that in there, H2O2, 0. All right, So this is, we've almost gotten to 1 half-life, but not quite. So ln of 0.1. All right, and so what I end up with is the natural log of this hydrogen peroxide at 15 minutes is going to be equal to negative 2.91. And then we're going to put that to get rid of the natural log. And I get 0.0542 molar. And that does look like it would make sense. It's not exactly half of what we had, which was that 0.1. It's a little bit more than that half. Let's go back to the question. Yes. So after one half-life, we had a 0.05 molar of my hydrogen peroxide, but we haven't gone a full 17 minutes. All right. So that is another first-order half-life reaction. And using that integrated rate law and how they're all interrelated. So now let me show you a second order rate law problem. We won't have to deal with half-life in those, so that's a little good. We have this reaction, and they do tell us that it is second order, and they tell us that the rate constant, K, is this, and under certain conditions. If the initial concentration of this guy, so this is C4H60, what is the concentration remaining after this time? So we notice our times in minutes, so is our rate constant, so we don't have to do any conversions there. And it is a second order reaction, so we are going to use that integrated rate law for second order. And that's going to show us that C4H6, 1 over the concentration of that equals K times T plus 1 over the initial concentration. C4H60. All right, and then we'll just plug things in here. So my rate constant is 5.76 times 10 to the negative 2. This is 1 over molarity minute times time, which is 10 minutes, plus 1 over that initial concentration, which is 0.2. With all of that, I end up with 1 over C4H6 is equal to 5.58, but I don't want 1 over the concentration. I want just the concentration. So I am just going to invert my answer. So you can have your answer in there, and on your calculator, press the X-1 button, and it will find the inverse of that. So in doing that, C4H6 is equal to 5.58 to the negative 1, which is 0.179 molar. And again, that makes sense. We've had some time go by. It should be less than our initial concentration. And that's how you work with second order integrated rate law.